The universe is expanding at 70 kilometers per second for every megaparsec of distance. That means two galaxies separated by 3.3 million light-years are racing apart at 70 kilometers per second, double the distance, and the speed doubles too. Push far enough out and galaxies recede faster than light itself. This discovery came from Edwin Hubble in 1929, measuring the redshift of 46 galaxies with a telescope on Mount Wilson. His observations shattered the belief in a static, eternal cosmos. Einstein called his own cosmological constant his biggest blunder. But Hubble's discovery created a paradox that haunts physics to this day. If the universe is expanding, it must be expanding into something. Yet nothing exists beyond the universe by definition. The universe contains all space, all time, all matter, all energy. There is no outside. There is no beyond. The question itself seems to break logic. Scientists have wrestled with this contradiction for nearly a century, and the answer reveals something far stranger than empty space waiting to be filled. If you are ready to see the universe differently, hit that like button and subscribe. We begin now. Think about a balloon. You blow it up and it expands into the room. The rubber pushes outward. The air inside fills a space that was already there. Your lungs force breath into latex, and the balloon gets bigger by displacing the air around it. That air was there first. The balloon just moved into it. Every expansion you have ever witnessed works this way. Cities grow outward into countryside. Wildfires spread into forests. Even explosions in space, those silent blooms of debris from dying stars, expand into the vacuum. There was vacuum first. Then, the explosion filled it. This is how expansion works in your experience. Something grows by occupying space that already existed before it arrived. Your brain learned this rule before you could walk. Objects move into space. Space itself just sits there, empty and waiting. This mental model is so deeply wired into your thinking that you cannot perceive expansion any other way. When someone says the universe is expanding, your mind immediately asks the obvious question. What is it expanding into? The question feels natural, logical, necessary. When you ask what the universe is expanding into, you are asking a question that has the same logical structure as asking what is north of the North Pole. The words make sense. The grammar is fine. The sentence is perfectly constructed. But you have just tried to use a concept that only works inside the system to describe something outside the system. This is what kept me awake one night, realizing that some questions do not have answers because the questions themselves are broken. The question is not unanswered. The question is physically meaningless. It belongs to the same category as asking what blue smells like or what direction Thursday is. These questions have grammatical structure. They follow the rules of language, but they assume a framework that does not exist. Color does not have scent. Days of the week do not have spatial orientation, and the universe does not expand into anything because there is no container for it to expand into. The mistake is subtle but fundamental. You are thinking of the universe as an object, a thing that exists in space, like that balloon in the room. That balloon is made of rubber. It floats in air. The air surrounds it. The room contains both. The house contains the room. The earth contains the house. You can keep zooming out, container after container, until you reach the universe itself. Then your brain expects one more container, one more outside. There is no outside. The universe is not an object in space. The universe is space itself. Space is not a container that holds things. Space is the fabric on which reality is written. When the universe expands, space itself grows, not into anything, not displacing anything, just more space where there was less space before. Picture dots drawn on the surface of a balloon. Forget the three-dimensional balloon for a moment. Pretend you are a flat creature living on that two-dimensional surface. You can move forward, backward, left, right, but up and down do not exist for you. You cannot perceive them. You cannot conceive of them. Your entire reality is the surface. The balloon inflates. The dots move apart. From your perspective on the surface, the distance between dots increases. You measure it. You confirm it. The dots are separating. Your natural question is this: what are we expanding into? But the answer is nothing. The surface itself is stretching. There is no three-dimensional room for flat U to expand into. The question assumes a dimension that is not part of your reality. You are not a flat creature on a balloon, but you are a creature embedded in space, asking what space is expanding into. The question assumes something outside space. There is nothing outside space. Outside does not exist as a concept here. Consider train stations on a stretching track. The stations do not move. They sit perfectly still on the track, but the track itself grows longer between them. A train leaving one station takes longer to reach the next station, not because the stations moved, but because more track appeared between them. The stations represent galaxies. The track represents space. Galaxies are not flying through space away from each other. Space itself is growing between them. The galaxies just sit there while the distances increase. Here is another way to see it. Imagine graph paper where the squares themselves enlarge. You draw galaxies on the paper. The galaxies stay the same size, but the squares of the grid grow bigger. The distance between galaxies increases because the grid stretched. The grid is space. The drawings are galaxies. Space expanded. The galaxies did not move. Your intuition screams that this is impossible. That expansion requires a destination. That growth demands a container. But your intuition evolved to navigate a savanna, not a cosmos. Your brain developed to throw spears and climb trees and recognize faces. It did not develop to understand the fabric of space-time. The universe does not care what you find intuitive. The breakthrough comes when you stop thinking of space as nothing. Space is not just the absence of things. Space has properties. It can bend. It can ripple. It can stretch. When scientists say the universe is expanding, they mean space itself is increasing in extent, not moving into some pre-existing void, just becoming more of itself, more space where there was already space. This is the foundation. The universe is not expanding into anything because there is no anything for it to expand into. The question assumes a framework that reality does not have. It assumes an outside when outside is not a meaningful concept. It assumes space is a container when space is the thing itself. What actually happens during expansion is stranger and more elegant than empty space waiting to be filled. The mechanism has nothing to do with edges or boundaries or containers. It has everything to do with the nature of space itself and what happens when that nature changes over time. That is where we go next. The previous section told you that space has properties, that it can bend and ripple and stretch. But what does that actually mean? What happens when space stretches? Think about measuring something with a ruler. You put one end at 0, the other end tells you the distance. Simple. That works because the ruler stays the same size while you measure. The ruler is fixed. The space between the marks does not change. Space-time does not work that way. In 1915, Einstein's general relativity revealed something profound. Space and time are not separate things. They form a single fabric with measurable properties. That fabric can curve around massive objects. It can ripple when black holes collide. And it can stretch. The stretching is not a metaphor. It is a physical change in the structure of space-time itself. Physicists describe this with something called the metric tensor. That sounds technical because it is, but the concept is simple. The metric tells you the distance between 2 points in space. It is the ruler. When the metric changes, distances change. Not because anything moved, because the ruler itself transformed. Imagine measuring a table with a rubber ruler. You place it down, read the measurement, but while you are reading, the ruler stretches. The table stretches with it. The space between the marks on the ruler grows. So does the space in the table. You would never notice from inside this system. The ratio stays the same. But to someone outside watching, everything got bigger. There is no outside to the universe. We are all inside, measuring with rulers that stretch along with space. We only know expansion is happening because we can look at distant objects and see how the stretching affects light traveling toward us. The metric is changing. The distances are growing. and we have measured exactly how fast. Right now, space expands at approximately 73 kilometers per second for every megaparsec of distance. A megaparsec is 3.26 million light-years. That is an almost incomprehensible span. Picture our entire galaxy, the Milky Way. Now imagine 65,000 of them laid end to end. That is 1 megaparsec, and every single megaparsec of space stretches by 73 kilometers every second. That number seems small against such vast distances. 73 kilometers is about the distance from one side of a city to another, every second, for every 3.26 million light-years. But it compounds. A galaxy 10 megaparsecs away sees space expanding at 730 kilometers per second. 100 megaparsecs, 7,300 kilometers per second. The farther away something is, the faster the space between us grows. Two ants standing on opposite ends of a rope. The rope stretches. Both ants stay completely still relative to the rope beneath their feet. They are not walking. They are not moving. But the distance between them increases. The rope is growing. They are just standing there while it happens. This is the surprise that shifts everything. Galaxies are not moving through space. They are sitting still. Space is growing between them. A galaxy 100 million light-years away is not hurtling away from us. It carries no momentum. It has no kinetic energy from expansion. It is stationary in its local patch of space-time. That patch is simply getting farther from our patch. The gap widens while both galaxies remain motionless. Think about that. Every distant galaxy we see, receding at thousands of kilometers per second, is not actually moving. Not in the way a car moves down a highway or a planet orbits a star. Those involve motion through space. Expansion is different. It is the changing of space itself. Picture a film projector showing a movie. Normally, images move across fixed frames. One frame shows a person on the left. The next frame shows them in the middle. The next on the right. That is motion through space. Now imagine something stranger. The person stays in the exact same spot on every frame, but the frames themselves expand. The borders stretch outward. The person does not move within the frame. The frame grows around them. That is metric expansion. The metric tensor, the mathematical description of distances, evolves with time. Every second, the numbers change slightly. The amount of space between any 2 points that are not bound together by gravity increases. Not because those points moved, because the space connecting them became more space. You cannot feel this happening locally. Gravity holds galaxies together. It holds solar systems together. It holds you together. The expansion only wins across distances so vast that gravity becomes too weak to resist. Between galaxy clusters separated by hundreds of millions of light-years, space wins. It stretches, and those clusters drift apart without ever moving at all. This is what expansion means. Not stuff spreading into a container. Not galaxies flying outward from some central point. Just the ongoing, relentless increase in the metric that defines distance. More space appearing where space already existed. The universe becoming larger, not by growing into anything, but by the fundamental nature of space-time changing as time moves forward. We know this is happening. We have measured it. 73 kilometers per second per megaparsec. That number has profound consequences. It tells us where the universe came from. It tells us where it is going. And it reveals something unexpected about the shape and fate of everything that exists. But the universe expanding does something you might not have considered. It does something to light itself, and that changes everything about what we can see. When a photon leaves a distant galaxy and travels through space toward us, it exists in that space. The space it moves through is not fixed. That space is stretching while the photon crosses it. The photon does not speed up or slow down. Light always moves at light speed, but the space the photon occupies gets larger. And when space stretches, the photon stretches with it. The wavelength increases. Blue light becomes green. Green becomes red. Red becomes infrared. Infrared becomes microwave. The photon loses energy not because something absorbed it, but because the metric of space itself changed during its journey. This is cosmological redshift. It is not the Doppler effect. The Doppler effect happens when something moves toward or away from you through space, a siren changing pitch as an ambulance passes. That is motion through a fixed medium. Cosmological redshift is different. The source is not moving through space. The space between the source and you is becoming more space. The photon is not being compressed or stretched by motion. It is being stretched by the expansion of the fabric it travels through. Picture a photon as a hiker on a treadmill. The hiker walks forward at a steady pace, but the treadmill moves backward, and the treadmill speeds up the farther away you get. The hiker is moving, making progress, walking toward the goal, but the goal is receding faster than the hiker can approach. The hiker gets farther from where they started, and also farther from where they are trying to go. That photon is still traveling, still covering distance, but the distance to cover keeps increasing. The most distant galaxies we have observed have redshift values above z equals 10. That means the wavelengths of light we receive have been stretched more than 11 times their original length. A photon that left as ultraviolet light arrives as deep infrared. We do not see these galaxies with visible light telescopes. We cannot. The light that left them as visible photons arrives as something our eyes cannot detect. Only infrared sensors can capture them. The universe has transformed the light itself during its journey. The farther away a galaxy is, the more space its light crosses. The more space it crosses, the more that space expands during the journey. The more space expands, the more the light stretches. At a certain distance, the photons stretch so much, they carry almost no energy at all. They arrive as faint radio waves, whispers of light that once blazed bright. But there is a threshold, a point beyond which light does not just stretch, it never arrives at all. There exists a distance, currently about 63 billion light-years away in moving coordinates, beyond which light emitted today will never reach us. Not in a billion years, not in a trillion, never. The space between us and that light is expanding faster than the light can cross it. The photon moves toward us at light speed, but the finish line recedes faster than light speed. Not because the photon slows down, because more space appears between here and there while the photon is in transit. Think of it as mailing a letter. You write someone's address on the envelope. You send it, but while the letter is traveling, the recipient's address changes. The postal system updates the destination. The letter keeps moving, keeps being forwarded, but the destination keeps changing faster than the letter can arrive. The letter is never lost. It is always in transit, but it will never be delivered. That is happening right now. Photons that left distant galaxies aimed directly at Earth. Photons that have been traveling for billions of years. They are still traveling, still moving through space at the speed of light, still headed in our direction. They will never arrive. They exist in the space between, getting farther from their source galaxy, also getting farther from us, traveling forward through expanding space that stretches faster than they can cross it. They are in perpetual journey, forever in transit. They left home. They will never reach their destination. They are just out there, in the dark, moving through a void that grows faster than they can traverse it. There are galaxies beyond that horizon, galaxies with stars and planets, maybe civilizations, maybe someone looking up at their sky, wondering what lies beyond. The light from those galaxies will never reach us, not because something blocks it, not because it fades or scatters, because the universe itself prevents the delivery. The structure of space-time makes it impossible. You can imagine trying to count grains of sand on a beach. You count steadily, 1 grain per second. You are making progress. But the beach is growing. New sand appears faster than you can count. You count 1,000 grains. The beach adds 10,000. You count 1,000,000. The beach adds 1,000,000,000. You never stop counting. You never slow down. But the total grows faster than you can measure. You are working, making progress, and falling farther behind every second. That is what happens to light from beyond the cosmic horizon. It travels. It moves toward us. And it falls farther behind. This is not theoretical. We know the expansion rate, 73 kilometers per second per megaparsec. That is about 73 kilometers per second for every 3.3 million light-years of distance. At a certain distance, the accumulated expansion rate exceeds the speed of light, not locally. No point in space moves faster than light through its local region. But the sum total of all the expanding space between here and there adds up to more than light can overcome. The photon climbs. The hill grows faster. There are things in this universe we can never see, not because they are hidden behind something, not because our telescopes are not powerful enough, because the universe itself has placed them beyond reach. The light they emit is out there, traveling, aimed at us, and we will never receive it. It will never arrive, not because it stops, because it cannot cross the space that keeps expanding between us. The universe has an edge we cannot see past, not a physical edge, an informational one, a horizon beyond which no signal can reach us, no light, no radiation, no information of any kind. There could be a galaxy out there identical to ours. There could be planets with oceans and life. There could be someone wondering if they are alone, and we will never know. They will never know about us. The universe has separated us not by distance alone, by something more fundamental, by the structure of reality itself. Some of those photons have been traveling since before Earth formed, before the sun ignited, before our galaxy settled into its current shape. They have been crossing space for 10 billion years, still crossing it, still moving at light speed, and they are farther from us now than when they started. They will travel forever through an expanding void, never arriving, never stopping, just moving through more and more space that appears in front of them, faster than they can cross it. That is what expansion does to light. It stretches it, it delays it, and beyond a certain distance, it prevents it from ever arriving. There is a boundary to what we can ever know, not because of technology, not because of time, because the universe is expanding, and some things lie beyond the horizon that expansion creates. The universe is expanding because something is pushing it apart. That something has a name: dark energy. We discovered it in 1998. Two teams of astronomers were studying distant supernovas, type Ia supernovas to be specific. These explosions are special because they always shine with the same brightness. That makes them cosmic measuring sticks. You can compare how bright they should be with how bright they appear, and that tells you how far away they are. The teams were using them to measure the expansion rate of the universe. They expected to find the expansion slowing down. Gravity should be pulling everything back together, right? Slowly, perhaps, but slowing nonetheless. That's not what they found. The expansion was speeding up. The universe wasn't just expanding, it was accelerating, getting faster over time. That discovery won the Nobel Prize because it completely upended our understanding of what's happening to space. Something was overpowering gravity. Something was pushing galaxies apart with more and more force. We call it dark energy, but that name is just an admission. We don't know what it is. We know what it does. It pushes. Unlike gravity, which pulls, dark energy has what physicists call negative pressure. It drives things apart, and here's what makes it dominant. Dark energy makes up 68% of everything in the universe. Dark matter, the invisible stuff that holds galaxies together, makes up 27%. All the ordinary matter, every star, planet, atom, and photon, every galaxy we can see, that's just 5%. 5%. Everything you've ever seen or touched or thought about is a rounding error in the cosmic budget. The rest is dark energy, and it's winning. Here's why. When the universe expands, matter spreads out. Take a cubic meter of space containing 1,000 particles, double the volume, and now you have 1,000 particles in 2 cubic meters. The density drops by half. Dark matter works the same way. It dilutes as space grows, but dark energy doesn't dilute. Its density stays constant, approximately 6 times 10 to the negative 10th joules per cubic meter. That number doesn't change no matter how much the universe expands. Think about what that means. If the universe doubles in volume, the amount of matter stays the same. It just spreads out, but the amount of dark energy doubles, because you now have twice as much space, and dark energy is a property of space itself. It's not a substance filling the void. It is the void. Empty vacuum has energy. The more vacuum you have, the more dark energy you have. Picture your monthly budget. Gravity is your salary. It stays fixed. Dark energy is your rent. And every year your rent goes up while your salary stays the same. At first, you can manage. Salary dominates. You have money left over. But as rent keeps climbing, it takes a bigger and bigger share. Eventually, rent dominates everything. There's nothing left for anything else. That's what's happening to the universe. The dark energy budget is growing. The gravity budget is fixed. And dark energy is taking over. This process has been running for roughly 5 billion years. Before that, the universe was smaller. Matter was denser. Gravity was strong enough to slow the expansion down. The universe was still growing, but decelerating. Then, about 5 billion years ago, the universe expanded enough that dark energy took over. The density of matter dropped below a critical threshold. Dark energy became dominant, and the expansion started accelerating. It's been accelerating ever since, getting faster every moment, and it will never stop, because the mechanism is self-reinforcing. Expansion creates new space. New space contains more dark energy. More dark energy drives more expansion, which creates more new space. It's not a fuel that runs out, it's a fuel that multiplies. Imagine you're trying to collect water from a faucet. You have a bucket. You're filling it slowly, but every minute, someone installs another faucet, then another, then another. You're not fighting a fixed flow anymore. You're fighting a growing opponent, an opponent that gets stronger the longer you fight it. That's what gravity is up against. It's not losing to a constant force. It's losing to a force that increases every time space expands. There's another way to see this. Think about light traveling through the expanding universe. A photon leaves a distant galaxy and heads toward us. As it travels, space expands. The wavelength of the photon stretches along with space. By the time it reaches us, the light has shifted toward the red end of the spectrum. We call this cosmological redshift. It's like an audio recording played on a tape that's stretching while you listen. The pitch drops, not because the sound changed, but because the medium changed. The tape got longer, so the wavelengths got longer, so the pitch got lower. That's what expansion does to light. It stretches it. The farther the light travels, the more space expands along the way, the more the light gets stretched. We can measure that stretch. It tells us how much the universe has expanded since the light was emitted. And when we measure light from very distant supernovas, we see more stretching than we expect. More than there would be if expansion were constant. More than there would be if expansion was slowing down. The only explanation is that expansion is speeding up, and it's dark energy making that happen. This mysterious property of empty space. This thing we can't see, can't touch, can't even properly define. It makes up more than 2/3 of everything that exists, and it's growing. The expansion has been accelerating for 5 billion years. It will keep accelerating for trillions more. Dark energy will keep increasing. Matter will keep diluting. The gap will keep widening. Eventually, dark energy will dominate so completely that gravity becomes irrelevant on cosmic scales. Galaxies will be pushed apart faster and faster. The space between them will grow at accelerating rates. Things that are gravitationally bound, like our local galaxy cluster, will stay together, but everything else will recede beyond reach. Dark energy is not temporary. It's not a phase. It's the future of the universe. Permanent, accelerating, unstoppable. The universe isn't just expanding into some abstract notion of nothing. It's expanding because of nothing, because empty space itself has this intrinsic property that pushes everything apart. And the more space there is, the stronger that push becomes. We are living in the transition era, the brief cosmic moment when matter and dark energy are roughly balanced, when we can still see distant galaxies, when light from the early universe can still reach us. 5 billion years ago, matter dominated. 5 billion years from now, dark energy will dominate even more completely than it does now. We're in the middle, the brief window when both forces matter. That's what's driving expansion. That's why it's accelerating. That's why it will never stop. Dark energy isn't fighting gravity to a standstill. It's winning, and the victory is already decided. So we know dark energy is pushing everything apart. We know the expansion is accelerating. We know the universe's fate is sealed, but how do we actually know any of this? The entire story of cosmic expansion rests on a single measurement: distance. How far away is that galaxy? How far was it a billion years ago? How much farther is it now? Everything depends on measuring distance across the void, which turns out to be a harder problem than you might think. We've never directly measured the distance to any galaxy. Not one. Not even our nearest neighbor. There's no cosmic tape measure. No radar signal that could reach another galaxy and bounce back. Even if you sent a light beam to the nearest galaxy beyond our own, it would take 2.5 million years to get there, and another 2.5 million years to return. You're not waiting for that measurement. Every cosmic distance is an inference. We measure light, brightness, color, pattern. Then we work backwards to calculate how far away the source must be. The entire cosmic distance scale rests on assumptions about how light behaves. Assumptions that could, in principle, be wrong. Think about standing on a shore at night. You see a boat's light in the distance. How far away is it? If you know how bright the light actually is, you can compare that to how dim it appears. Dimmer means farther, but you have to know the true brightness first. You have to know what you're looking at. Astronomers call these objects standard candles, things in the universe with known consistent brightness. If you know how bright something truly is, and you measure how bright it appears from Earth, you can calculate the distance. The math is straightforward. Finding reliable standard candles is not. The best standard candle we have is a stellar explosion called a Type 1 a supernova. These happen when a white dwarf star steals matter from a companion star. The white dwarf grows heavier and heavier. Eventually, it hits a specific mass limit, about 1.4 times the mass of our Sun. At that exact threshold, the star detonates. Every single time. Same mass, same explosion, same peak brightness. Type 1. A supernovae shine with the light of about 5 billion suns. That's bright enough to outshine an entire galaxy for a few weeks. Bright enough to be seen across billions of light years. And because they always reach the same mass before exploding, they always release roughly the same amount of energy. They're consistent, reliable, perfect distance markers. You spot a Type 1 a supernova in a distant galaxy. You measure how bright it appears. You know how bright it actually is. The difference tells you the distance. The universe itself has given you a ruler that works across cosmic scales. But there's a problem. Type 1. A supernovae are rare. You can't just order one up when you need a distance measurement. You have to wait. Watch millions of galaxies. Hope one happens while you're looking. And even when you find one, you need to know it's actually a Type 1a and not some other kind of explosion. You need to verify its brightness, calibrate it. That calibration requires knowing the distance to closer objects first. Objects near enough that you can use other methods. This is where the cosmic distance ladder comes in. Picture measuring a very tall building, too tall to measure directly. So you stack measuring sticks. You measure the first floor with a meter stick. Use that to calibrate a longer pole. Use the pole to measure 10 floors. Use those 10 floors to calibrate an even longer method. Stack techniques, each building on the previous one. Each rung of the ladder depends on the rung below it. If your first measuring stick is slightly wrong, the error multiplies. By the time you reach the top of the building, you're off by meters, maybe more. The ladder works, but only if every rung is solid. The cosmic distance ladder starts with parallax, the apparent shift in position when you view something from different angles. Hold your finger in front of your face and close one eye, then the other. Your finger seems to jump. That jump gets smaller the farther away the object is. Earth's orbit around the Sun gives us two viewing angles, 6 months apart. For nearby stars, we can measure that tiny shift, calculate distance directly. No assumptions needed. Parallax works out to about 3,000 light years. Beyond that, the shift is too small to measure, even with our best instruments. That's rung 1. 3,000 light years in a universe 93 billion light years across. Rung 2 is Cepheid variable stars. These stars pulse, brighten and dim in a regular rhythm. And here's the key. The period of the pulse is directly related to the star's true brightness. A cepheid that pulses every 10 days is brighter than one that pulses every 3 days. Always, every time. You measure the pulse period. That tells you the true brightness. Compare to the apparent brightness. Calculate distance. Cepheids can be seen up to about 100 million light-years away, far enough to reach nearby galaxies, far enough to calibrate the next rung. But you have to calibrate the cepheids first. You need to know the relationship between pulse period and brightness. To establish that, you need cepheids close enough to measure with parallax. You need rung 1 to build rung 2. Rung 3 is type 1 a supernovae. You find supernovae in galaxies close enough to contain measurable cepheids. The cepheids give you the galaxy's distance. The supernova's apparent brightness at that known distance tells you its true brightness. Now you've calibrated your standard candle. Now you can use type 1a supernovae to measure distances billions of light-years away. Each rung depends on the one below. Parallax calibrates cepheids. Cepheids calibrate supernovae. Supernovae measure cosmic expansion. If any step is wrong, everything above it shifts. The ladder holds together, but it's more fragile than it looks. There's another technique, another way to measure cosmic distances that doesn't rely on brightness at all. It uses sound, or rather, the fossil evidence of sound waves from the early universe. In the first few 100,000 years after the Big Bang, the universe was hot plasma, dense enough that pressure waves could travel through it, sound waves on a cosmic scale. These waves rippled outward from density fluctuations, creating shells of slightly higher density. When the universe cooled enough for atoms to form, the sound waves froze, stopped in place. The pattern they left behind is still visible today. Galaxies tend to cluster at a specific distance from each other, roughly 490 million light-years apart. That's the radius where those ancient sound waves stopped. Astronomers call this pattern baryon acoustic oscillations. It's subtle, a slight statistical preference in galaxy positions, but it's measurable, and it's always the same scale, 490 million light-years. The universe has expanded since those sound waves froze, stretching the pattern along with it, but the ratio stays constant. It's a standard ruler instead of a standard candle. You look at the apparent size of the clustering pattern, compare it to the known true size, work out the distance. Baryon acoustic oscillations don't depend on brightness, don't require rare explosions. They're everywhere. Galaxies exist. They're a completely independent check on the distance ladder. A second method, a second way to measure how fast the universe is expanding. Two methods, both sophisticated, both tested over decades. Both should give the same answer. They don't, not quite. And that disagreement is about to become a problem. The problem appeared gradually, then suddenly. For years, scientists refined their measurements. They built better telescopes, better satellites, better computers to analyze the data. Each improvement made the numbers sharper, more precise. They expected the measurements to converge, to settle on a single answer for how fast the universe is expanding. Instead, the answers split apart. Local measurements, ones using the cosmic distance ladder, Cepheid variables, and type Ia supernovae to map distances to nearby galaxies. These give a Hubble constant of 73.04 kilometers per second per megaparsec. That means for every 3.3 million light-years of space, the expansion adds another 73 kilometers per second. The uncertainty is small, plus or minus 1.04. These measurements are precise. Early universe measurements tell a different story. The Planck satellite mapped the cosmic microwave background, the afterglow of the Big Bang. It measured the universe as it was 380,000 years after it began. From those patterns, you can calculate how fast the expansion should be today. The answer comes out to 67.4 kilometers per second per megaparsec. Same units, same measurement, different number. The uncertainty here is even smaller, plus or minus 0.5. Both methods are sophisticated. Both have been tested, refined, checked and rechecked. Both should agree. They don't. The difference is 9%. That might sound small. It's not. Imagine you have two thermometers. Both are precision instruments, both calibrated by experts, both measuring the same room at the same time. One reads 70 degrees, the other reads 64. One says it's comfortable, the other says you need a sweater. Both can't be right, but both are too precise to be accidents. Or, think of it this way. You measure your height in the morning, 6 feet tall. You measure again in the evening, 5 feet 6 inches. Either you're measuring wrong, or something very strange is happening to your spine. That's the situation cosmology is in right now. The discrepancy has a name, the Hubble tension. Astronomers chose that word carefully. Not disagreement, not uncertainty, tension. Something pulled tight, something that might snap. Statistical significance measures how likely a result is due to chance. Scientists use a scale called sigma. 1 sigma means there's about a 30% chance the difference is random noise. 2 sigma drops that to 5%. 3 sigma is 0.3%. By the time you reach 5 sigma, the chance of coincidence is less than 1 in a million. That's the threshold physicists use to declare a discovery. The Hubble tension is now between 5 and 6 sigma. The odds that this discrepancy is a fluke are vanishingly small. This is real. Something is wrong, either with our measurements or with our understanding of how the universe expands. Here's the thing that makes this a crisis, the thing that keeps cosmologists up at night. More data hasn't helped. Better measurements haven't closed the gap. They've widened it. Every time someone refines the local distance measurements, the number stays stubbornly around 73. Every time someone reanalyzes the cosmic microwave background, it stays around 67. The precision improves. The disagreement remains. This is backwards from how science usually works. Usually, early measurements are crude, imprecise. They disagree because the tools aren't good enough yet. As technology improves, the measurements converge. The error bars shrink until everyone agrees on the same number. That's not what's happening here. The error bars are shrinking. The numbers aren't coming together. The crisis isn't that we don't know the expansion rate. It's that we know it too precisely in 2 different ways, and the answers don't match. Think about what this means. One of 3 things must be true. Either there's a systematic error in one of the measurements, something subtle that everyone has missed despite decades of checking, or the early universe had different properties than our models predict. Something about those first 380,000 years was different, or the expansion rate has changed over cosmic history in ways the standard model doesn't account for. That third option is the most unsettling. The standard model of cosmology includes dark energy, an unknown force pushing the universe to expand faster and faster. The model assumes dark energy has been constant, the same strength throughout cosmic history, same effect, same acceleration. If the Hubble tension is real, that assumption might be wrong. Dark energy might be evolving, changing strength over billions of years, getting stronger, or weaker, or varying in ways we haven't imagined. Some cosmologists think the problem is with the cosmic microwave background measurements. Maybe the universe wasn't exactly uniform in those early moments. Maybe there were subtle variations that throw off the calculations. Others think the distance ladder has hidden errors, some rung. We trust that's actually slightly off. Still others think both measurements are correct, that the universe really is expanding at different rates in different epochs, or different places. Multiple independent teams have checked both methods, used different telescopes, different samples of stars and supernovae, different analysis techniques. The local measurements keep coming back around 73. The early universe measurements keep coming back around 67. The tension holds. There's another possibility, one that's harder to accept. Maybe our entire cosmological model is incomplete. Maybe there's something missing from our understanding of gravity, or dark matter, or the fabric of space itself. Something fundamental that we haven't discovered yet because we've never needed it to explain our observations. Until now. The universe doesn't care what we find convenient. It doesn't adjust itself to match our models. If our best measurements disagree, the universe isn't wrong. We are. Baryon acoustic oscillations provide a third way to measure expansion. That standard ruler frozen into the distribution of galaxies. Those measurements fall somewhere in between the other 2, closer to 67 than 73. They don't resolve the tension. They add another data point to a puzzle that refuses to make sense. The Hubble constant isn't just a number. It tells us the age of the universe, how long ago the Big Bang happened. It tells us the distances to the farthest galaxies. It tells us how much time we have before expansion tears everything apart. Getting it wrong means getting all of that wrong. The stakes are higher than just an academic disagreement. Some scientists are starting to wonder if this is a hint, a crack in our understanding wide enough to see through, the kind of discrepancy that precedes a revolution. When measurements refused to match predictions in the early 1900s, it led to quantum mechanics, to relativity, to a complete overhaul of physics. Maybe we're standing at another threshold like that. Maybe the Hubble tension is telling us something profound about reality. We just haven't figured out what yet. For now, the tension holds. Two numbers, both precise, both trusted, both impossible to reconcile. One suggests the universe is younger and expanding faster than we thought. The other suggests our models from the early universe are correct and something else is wrong. Both can't be right. The question isn't whether there's a problem anymore. The question is what that problem is trying to tell us. What are we missing? What piece of the puzzle sits just outside our current understanding, waiting to make everything fit? The answer might change everything we think we know about what dark energy actually is. Here's what makes this so strange. We've measured dark energy's effects to incredible precision. We know how it behaves. We know what it does. We know it makes up 68% of everything that exists. But we have absolutely no idea what it actually is. Think about that for a second. 68% of reality, the dominant component of existence. You could compare this to discovering that 68% of your body is made of a substance you've never heard of and can't detect directly. Something that's been there your entire life, governing how you move and grow, completely invisible to every test you've ever taken. That's where we are with dark energy. We've given it a name. We've built mathematical models that describe its behavior perfectly. We've measured its influence across billions of light years. But the fundamental question remains unanswered. What is it? What's actually out there, pushing space-time apart? The most straightforward answer is called the cosmological constant. This treats dark energy as a fundamental property of space-time itself. Not a thing in space, not a force acting on space, just a feature built into the fabric of reality. Empty space has energy. That energy never changes. It can't be created or destroyed or diluted. When the universe expands and creates more space, it creates more of this energy. The density stays constant forever. Einstein actually proposed this idea back in 1915. He called it lambda. He added it to his equations of general relativity to keep the universe static, because everyone assumed the universe wasn't expanding. When expansion was discovered, he abandoned it, called it his biggest blunder. Turns out he might have been right the first time, just for the wrong reasons. The cosmological constant has an equation of state written as equals -1. That -1 is crucial. It means the pressure is negative. Negative pressure pulls instead of pushes, but in the geometry of space-time, that negative pressure creates a repulsive effect. It drives expansion. The math works perfectly. The observations fit. The problem is that the cosmological constant doesn't explain anything. It just says, this is how space-time is. It's a description, not an explanation. Other models try to dig deeper. Quintessence models propose that dark energy isn't constant at all. Instead, it's a dynamic scalar field that varies over time and space. Picture a field like electromagnetism, but one that fills all of space and has negative pressure. This field could change strength. It could evolve. Its equation of state might not be exactly -1. It might be -0.9 or -1.1, and it might shift as the universe ages. You can think of it like the interest rate on a cosmic mortgage. The cosmological constant is a fixed rate. It never changes. Quintessence is a variable rate. It could be higher now than it was in the past. It could be lower in the future. We're still paying the same kind of debt. Space still expands, but the terms might be shifting beneath us. The challenge is that current observations can't tell the difference. Dark energy's equation of state looks very close to -1. If it's varying, the variation is subtle enough that our instruments can't detect it yet. We'd need measurements 100 times more precise to see if quintessence is real or if the cosmological constant is the whole story. Then there's vacuum energy. Quantum field theory predicts that empty space isn't really empty. Virtual particles pop in and out of existence constantly. These quantum fluctuations should contribute energy to the vacuum. When physicists calculate how much energy this should produce, they get a number. That number is larger than the observed dark energy density by a factor of 10 to the power of 120. Let me put that in perspective. 10 to the power of 120 is a 1 followed by 120 zeros. If you tried to predict someone's height and you were off by this factor, you'd predict they were 1 inch tall and then find them tall enough that their head would reach past the moon, past the sun, past the orbit of Pluto, past the nearest stars, all the way to the Andromeda galaxy, 2.5 million light years away. That's how wrong the prediction is. Scientists call it the worst prediction in the history of physics. And that's not hyperbole. Nothing else comes close. Something is catastrophically wrong with either our understanding of quantum mechanics or our understanding of gravity, or both. The universe doesn't care what our equations say it should do. Some physicists have suggested we don't need dark energy at all. Maybe general relativity breaks down on cosmic scales. Modified gravity theories like FR, gravity or massive gravity, propose changes to Einstein's equations. These models try to produce accelerated expansion without adding any new energy component. Space expands faster, not because something is pushing it, but because gravity itself works differently when you're dealing with distances of billions of light years. The problem with modified gravity is that it has to match every other observation we have. General relativity works extraordinarily well on smaller scales. The orbits of planets, the bending of light around galaxies, the detection of gravitational waves. All of these match Einstein's predictions to absurd precision. Any modification has to preserve all of that while also explaining cosmic acceleration. It's a narrow path to walk. Most modified gravity theories stumble somewhere. We don't really know. That's the honest answer. Every physics model that tries to predict dark energy's value from first principles fails spectacularly. Every attempt to explain what it is runs into problems. We're left with something that works mathematically, fits the data, and tells us almost nothing about the underlying reality. The cosmological constant might be right. Dark energy might just be a number, a fixed property of existence with no deeper explanation. Quintessence might be real, a field we haven't figured out how to detect yet. Vacuum energy might be the answer if we can solve the catastrophic mismatch between prediction and observation. Modified gravity might explain everything without needing dark energy at all. Or it might be something else entirely, something we haven't thought of yet, a possibility that sits outside our current framework, waiting for someone to notice the pattern we're all missing. What we do know is how it behaves. We can map its effects across cosmic history. We can measure how much space expands and when. We can trace the influence of dark energy from the early universe to today and project it billions of years into the future. We're cartographers mapping a territory we can't see, drawing boundaries around something we don't understand. The universe is 68% mystery. The dominant component of reality is something we've named but never identified. We live in a cosmos where the majority of existence is a complete unknown, and we're trying to figure out what it's expanding into. We're trying to figure out what the universe is expanding into. But before we can answer that question, we need to deal with something that doesn't seem to add up. A paradox hiding in plain sight. The universe is 13.8 billion years old. That's the time since the Big Bang, measured with extraordinary precision. Light has been traveling through space for 13.8 billion years. So the most distant thing we can see should be 13.8 billion light years away, right? Light travels for 13.8 billion years. It covers 13.8 billion light years of distance. Simple math. Except the observable universe is 93 billion light years across. Not 13.8 billion, 93 billion. The edge of what we can see is 46 billion light years away in every direction. That's the radius. Double it and you get the full diameter. 93 billion light years from one edge to the other. That seems impossible. Light has only had 13.8 billion years to travel. How can we see things that are 46 billion light years away? Did the light travel faster than light? Did we break the cosmic speed limit? No, nothing broke. This isn't a contradiction at all. It's just that distance itself is more slippery than it seems. Think about ordering a package. You live 1 hour from the warehouse. The delivery truck leaves and starts driving toward your house. But while it's driving, your house keeps moving away from the warehouse. The ground itself is stretching, carrying your house farther out. The truck travels for 1 hour and arrives at your door. Mission accomplished. But when you check the distance between your house and the warehouse now, after delivery, it's 3 hours away. The truck didn't travel 3 hours. It only drove for 1. But the destination moved while it was traveling. That's what happened with light from distant galaxies. The light left a galaxy when it was much closer to us. It traveled through space for 13.8 billion years. But while it was traveling, space itself was expanding. The galaxy kept moving away from us the entire time. By the time the light arrived, that galaxy was much farther away than it was when the light started its journey. The most distant galaxies we can observe are now about 46 billion light years away. That's where they are right now, in the present moment. But when they emitted the light we're currently seeing, they were only about 3 to 4 billion light years away. The light traveled from something relatively close, but the source of that light has been receding the entire time. You're looking at something that was nearby when it sent the image, but that same thing is now incredibly distant. You're seeing the past of something close and the present of something far away simultaneously. The galaxy appears in your telescope as it was billions of years ago, young and nearby. But if you could teleport there instantly, you'd find it 46 billion light years away, aged and evolved. This is why we use 2 different kinds of distance. Light travel time distance tells you how long the light has been traveling, 13.8 billion years. That's the age of the light, the history it carries. Proper distance tells you how far away the source is right now, accounting for all the expansion that happened while the light was in transit, 46 billion light years. That's the current location. Comoving distance is another term for this. It's the distance measured in a coordinate system that expands with the universe. Imagine marking dots on a balloon with a ruler that stretches along with the rubber. The dots stay at the same comoving distance even as the balloon inflates, but their proper distance, measured with a rigid ruler, increases. Remember the balloon analogy from earlier? Draw 2 dots close together. That's a galaxy and us, shortly after the Big Bang. The galaxy emits light. Now start inflating the balloon slowly while the light travels across the surface. The light is moving, covering ground, making progress. But the balloon is also expanding underneath it. The destination dot is sliding away. By the time the light arrives, the 2 dots are much farther apart than when the journey started. Put some numbers on it. The dots start 3 inches apart. Light travels across the balloon surface at 1 inch per second. Without any expansion, the light would arrive in 3 seconds. But the balloon is inflating. After 3 seconds, the light arrives, but the dots are now 10 inches apart. The light traveled for 3 seconds, but the distance grew to 10 inches. Both numbers are real. Both are measuring something true. This is why the observable universe has an edge at 46 billion light years. That's the proper distance to the source of the oldest light we can see. Light from the cosmic microwave background, emitted 380,000 years after the Big Bang. That light has been traveling for 13.8 billion years. But the place it came from is now 46 billion light years away. The edge of the observable universe isn't a wall. It's not a physical barrier sitting out there in space. It's more like the horizon on an ocean. Stand on a ship and look out. You see a circle of water around you, ending at a horizon line. Sail toward that horizon for hours. You never get closer. The horizon moves with you. It's defined by your position and the limits of your vision. not by any feature of the ocean itself. The observable universe is the same. It's a sphere centered on us, defined by how far light has been able to travel since the Big Bang. Every observer in the universe has their own observable universe, centered on them. An alien 40 billion light-years away would see a different set of galaxies than we do. Some overlap with ours, some don't. Their horizon is centered on them. Ours is centered on us. You can't ever reach the edge of your observable universe because it's not a place. It's a limit defined by your position and the age of the universe. As time passes, light from more distant sources reaches us. The edge gets farther away. The observable universe grows, not because space is expanding into new territory, but because we're receiving light from sources whose light is only just now completing its journey to us. Every year, the observable universe gets about 1 light-year larger in radius. New light arrives. The horizon pushes outward. We see a tiny bit more of what was always there, previously hidden by the finite speed of light and the finite age of the cosmos. But here's the thing. The universe itself, the whole universe, is almost certainly much larger than the observable part, possibly infinite. We're seeing a sphere 46 billion light-years in radius, only because that's how far light has been able to travel, accounting for expansion. Beyond that edge, the universe likely continues. More galaxies, more stars, more space. We just can't see it yet. The light hasn't had time to reach us. Distance in an expanding universe isn't one number. It's a choice of measurement. How far away was it when the light left? How far away is it now? How long has the light been traveling? These are 3 different questions with 3 different answers, all of them correct, all of them describing the same galaxy. The paradox dissolves once you realize that distance and time are tangled together in a universe that's been stretching for 13.8 billion years. The light carries the age, the galaxy carries the distance, and we're standing here, looking out at a cosmos where the past is close and the present is far away, trying to figure out where all this space is actually going. Let's try to cross it. Let's imagine you wanted to travel from one edge of the observable universe to the other, 93 billion light-years. You already know that's impossibly far. The numbers from the previous section tell you that, but numbers on a screen don't make you feel the distance. So let's make it visceral. Let's calculate how long it would actually take. Start with walking. You walk at about 5 kilometers per hour, a comfortable pace, the kind of speed you maintain when you're strolling through a park or wandering around a city. At that pace, crossing the observable universe would take 1.05 times 10 to the 23rd years. That number is meaningless without context. Let me translate it. If you started walking when the first multicellular life appeared on Earth 600 million years ago, and you walked every single moment since then, never stopping, never resting, you would have covered 0.00000000001% of the distance. Not 1%, not a tenth of a percent. A decimal point followed by 10 zeros and then a 1. Walking won't work. Let's drive instead. A car on a highway moves at about 100 kilometers per hour, 20 times faster than walking. That should help. At highway speed, the journey takes 5.25 times 10 to the 21st years. Still incomprehensible. That's 5,000 billion years. The universe itself is only 13.8 billion years old. You'd need to repeat the entire history of the cosmos, from the Big Bang to now, 370 million times, and you still wouldn't be there. Fine. Let's fly. A commercial airplane cruises at about 900 kilometers per hour, fast enough to cross the Atlantic in a few hours. At that speed, crossing the observable universe takes 5.84 times 10 to the 20th years. We've shaved off an order of magnitude. We're making progress. Except we're not. The universe would die and be reborn 500 million times before you reach the other side. Every star would burn out. Every black hole would evaporate. The cosmos would fade into cold darkness, and you'd still be flying through the void, alone. This isn't working. Let's use the fastest speed ever achieved by a human spacecraft. Apollo 10 holds the record at 39,897 kilometers per hour. They were falling toward Earth when they hit that speed, screaming through the vacuum after leaving the moon. At that velocity, the journey takes 1.32 times 10 to the 19th years. Still, a billion years. Still longer than a trillion human lifetimes. Still so far beyond reach that the number might as well be infinite. What about Voyager 1? It's been traveling through interstellar space since 1977, moving at 17 kilometers per second, 61,000 kilometers per hour, the fastest object humans have ever sent into deep space. At Voyager's speed, you'd cross the observable universe in 1.6 times 10 to the 17th years. That's 160,000 trillion years. The sun will die in 5 billion years. You'd need 32 million dead suns, one after another, to mark the passage of time on this journey. All of these numbers share one thing. They're all impossible. Not just impractical. Not just beyond our current technology. Fundamentally, cosmically impossible. Because they all assume the universe holds still while you travel. It doesn't. Let's go faster. Forget rockets. Forget physics as we know it. Let's say you have a spacecraft that can travel at the speed of light, 300,000 kilometers per second, the fastest speed allowed by the laws of physics, the speed at which causality itself operates. Nothing with mass can actually reach this speed, but let's pretend. Let's give you infinite energy and a perfect engine and a ship that somehow moves at light speed without breaking the universe. At light speed, crossing 93 billion light years would take 93 billion years if the universe weren't expanding, if space held still and let you cross it. But space doesn't hold still, it expands. And here's where the journey becomes truly impossible. The farther you travel, the faster space expands between you and your destination. It's like running on a treadmill that accelerates the farther you go. You're running at the maximum possible speed, the speed of light, the speed of causality itself, and you're losing ground. There's a distance called the Hubble sphere. It sits about 14 billion light years away from us. At that distance, space expands so fast that the recession velocity equals the speed of light. Galaxies beyond the Hubble sphere are moving away from us faster than light can travel through space. Not because they're moving through space that fast, because the space itself is expanding. If you tried to reach one of those galaxies, even traveling at light speed, you'd never arrive, ever. The destination would recede faster than you could approach it. You'd travel forever through an expanding cosmos and never get closer. This is the part that breaks intuition. We're used to the idea that speed solves distance. Go fast enough and you can get anywhere. That's how the world works on human scales. That's how physics works when you're driving to the store or flying to another continent. But it's not how the universe works at cosmic scales. There is no speed fast enough. This isn't an engineering problem. It's not a matter of building better rockets or discovering new propulsion systems. You could have infinite energy. You could move at the speed of light itself, the absolute cosmic speed limit, and you would still fail. The universe expands faster than light can cross it. That's not a technological limitation. It's a fundamental property of space-time, written into the structure of reality itself. Some galaxies we can see right now, galaxies whose light has reached us, are already unreachable. We're looking at them. We're studying them. We're measuring their distance and their composition. And we will never, ever visit them. Not in a million years. Not in a trillion. Not with any technology that obeys the laws of physics. If humans had been traveling at light speed in a spacecraft since the first Homo sapiens appeared 300,000 years ago, we'd still be inside the Milky Way. Our own galaxy is about 100,000 light years across. 300,000 years of light speed travel would get you across the galaxy 3 times. The Andromeda galaxy, our nearest large neighbor, sits 2.5 million light years away. You wouldn't even be close. And Andromeda is right next door. It's in our local group. It's gravitationally bound to us. Compared to the scale of the observable universe, Andromeda might as well be in the same room. The universe is unimaginably large. That's the scale we've been circling around. That's what all these numbers are trying to capture. 93 billion light-years is so far that even hypothetical travel at light speed cannot cross it. Even moving at the maximum possible speed, obeying every law of physics, using infinite energy, you cannot reach the edge, because the edge moves away faster than anything in the universe can chase it. The journey cannot be made. Not slowly, not quickly, not at all. We've been talking about distance, space, the sheer size of the universe, and how impossible it is to cross. But there's another dimension to this that's even more unsettling. Time. Not just how long it would take to get somewhere, how long things have already been happening, how old the light is that we're seeing right now. Let's try a different kind of comparison. Counting. You can count one number per second, maybe faster if you're rushing. 1, 2, 3, 4. Keep that pace. Never stop. Never sleep. Start counting the moment the Big Bang happened, 13.8 billion years ago, and continue until right now. You know what number you'd reach? About 10 to the power of 17. That's a 1 with 17 zeros. It sounds like a lot. It is a lot. But the observable universe contains roughly 10 to the power of 24 stars. To count every star, you'd need the entire age of the universe multiplied by 10 million. You'd have to live through the Big Bang 10 million times over, counting continuously to finish. That's how many stars there are, and each one has been burning for millions or billions of years. Here's another way to think about it. The cosmic microwave background, the oldest light we can see, was released 380,000 years after the Big Bang. That light has been traveling for 13.8 billion years. When those photons started their journey, Earth didn't exist. The Sun didn't exist. The Milky Way was still forming, just clouds of gas beginning to collapse into stars. That light is older than our entire solar system. It's older than most of the stars you can see in the night sky. And it's everywhere. There are about 400 cosmic microwave background photons in every cubic centimeter of space around you right now. 400 in a space smaller than a sugar cube. You're swimming in them. They pass through your body constantly, billions per second. Each one has been traveling since 380,000 years after the Big Bang, carrying information about the infant universe. The oldest light in existence is invisible, silent, and everywhere. Think about what that means. You're standing in a sea of ancient light right now, always. Let's compress the timeline to make it easier to grasp. Imagine the entire history of the universe, all 13.8 billion years, condensed into a single calendar year. January 1st, midnight, the Big Bang happens. The cosmic microwave background is released on January 1st, still in the first day. The Milky Way starts forming sometime in late spring. Our solar system, the Sun and Earth, don't show up until early September. Life on Earth appears a few weeks later. Dinosaurs emerge on December 28th. They go extinct on December 30th. All of human civilization, everything we've ever built, every empire, every war, every piece of art, every word ever written, happens in the last 14 seconds before midnight on December 31st. 14 seconds. That's agriculture. That's cities. That's the pyramids, the Roman Empire, the Renaissance, the moon landing. All of it. 14 seconds out of an entire year. This is the part that gets me. Human civilization's entire timeline, from the first planted seeds to right now, is shorter than the time it takes light to cross the Andromeda galaxy. Andromeda is about 200,000 light-years across. Light takes 200,000 years to travel from one side to the other. Human civilization, all of recorded history, is maybe 10,000 years old. We haven't even existed long enough for light to cross a single galaxy. Not ours, not Andromeda, not any of them. We're not just small in space, we're barely a flicker in time. The galaxy we talked about earlier, GNZ 11, one of the most distant ever observed, has a redshift of 11.1. The light we see from it left when the universe was 400 million years old. That's 3% of the universe's current age. 3%. Imagine if you could only see a photograph of someone taken when they were 1 year old, and now they're 33. That's the version of the universe we're looking at when we observe GNZ 11. an infant, and the light has been traveling ever since, for over 13 billion years just to reach our telescopes. Every distant galaxy is a time capsule. The farther away it is, the older the image. We're not looking out into space. We're looking back through time. The universe is its own archive. Here's the thing that makes it even stranger. That ancient light, those cosmic microwave background photons passing through you right now, they outnumber almost anything you can imagine. If you placed one atom down every second, starting at the Big Bang and continuing until now, you'd have fewer atoms than the number of CMB photons in a teaspoon of space, roughly 400 million photons per cubic centimeter. A teaspoon holds about 5 cubic centimeters. That's 2 billion photons in a teaspoon. You accumulated atoms for 13.8 billion years, one per second, and you still don't have enough. The universe is not just old, it's saturated with evidence of how old it is. When we see a distant galaxy, we're seeing it as it was billions of years ago. The galaxy still exists, probably, but it's changed, it's aged, stars have died, new ones have formed, the whole structure has evolved. We'll never see what it looks like now. The light showing us the present version won't arrive for billions more years. By the time it gets here, if anything is still here to see it, that present will be ancient history too. We're always looking at ghosts. Every star, every galaxy, every photon, already gone, at least in the form we're seeing. And the gap keeps growing. The universe expands. The light has farther to travel. The images get older. You're standing in the present, surrounded by the past, watching light that left its source before your planet existed. And you can't see anything else. There is no present tense in astronomy. Only then, only what was. Special relativity sets a speed limit. Light moves at 299,792 kilometers per second. Nothing can move through space faster than that. No object, no particle, no information. The laws of physics forbid it. This has been tested, confirmed, measured to absurd precision. The speed limit holds, but there's a loophole. Relativity limits how fast things can move through space. It says nothing about how fast space itself can expand. Think about what that means. A galaxy isn't moving through space faster than light. The space between us and that galaxy is expanding. The galaxy is sitting still, more or less, in its local region of space. We're sitting still in ours, but the space in between grows. And that expansion has no speed limit. Space doesn't move. Space just becomes more of itself. This isn't a technicality. This is how the universe actually works. The recession velocity of a galaxy depends on its distance. The formula is simple. Velocity equals the Hubble constant times distance. The Hubble constant is about 70 kilometers per second per megaparsec. A megaparsec is 3.3 million light years. For every megaparsec of distance, add 70 kilometers per second to the recession speed. Do the math. At 4,200 megaparsecs, the recession velocity equals the speed of light. That's 13.7 billion light years away. We call this distance the Hubble sphere. Beyond the Hubble sphere, galaxies recede from us faster than light. They're not breaking any laws. They're just far enough away that the expansion between us and them outpaces light itself. Most of the galaxies we can see are beyond the Hubble sphere. Let that sink in. The majority of the observable universe is currently receding from us faster than light. This isn't some exotic edge case. This is normal. The most distant galaxies we've observed have recession velocities 2 to 3 times the speed of light. They're visible because the light left them long ago when they were closer. But now, at this moment, they're rushing away faster than light can travel. Picture a fish swimming upstream. The fish swims forward at its maximum speed. It's trying. It's giving everything it has. But the current flows faster than the fish can swim. The fish moves forward through the water, but the water carries it backward faster than it swims. Net result, the fish goes backward. The fish isn't moving backward through the water. The water is moving, and the fish is caught in it. Light from a galaxy beyond the Hubble sphere is that fish. The photons travel toward us at light speed. They're moving through space as fast as physics allows. but space itself expands faster than they can cross it. The photons make progress locally, moving from one region of space to the next, but the finish line recedes faster than they approach. They're swimming upstream in a current they cannot overcome. Here's the strange part. We can see these galaxies. The light reached us. So how did it escape if the expansion is faster than light? The answer is that space expansion isn't uniform in time. The universe expands, but the rate changes. In the past, when that light was emitted, the galaxy was closer. The expansion between us and it was slower. The photons started their journey in a region where the recession velocity was less than light speed. They made progress. As they traveled, they crossed into regions where expansion was faster. But by then, they'd already covered enough ground. They were already partway here. Eventually, they crossed back into regions where recession dropped below light speed again. And finally, they reached us. It's like running a race where the track stretches as you run. You start close enough that you can make progress. The track stretches, but you're fast enough to advance anyway. By the time you hit the section where the track stretches faster than you can run, you're already past the worst of it. You slow down relative to the finish line, but you don't stop. You keep inching forward, and eventually, the stretching slows, and you cross. Those photons crossed. We see the galaxies, but the galaxies themselves, right now, are beyond our reach. If you left today, traveling at the speed of light, aimed at one of those distant galaxies, you would never arrive. The space between you and the target would expand faster than you could cross it. You'd fly forward forever, covering trillions of kilometers every second, and the galaxy would recede faster than you approach. You'd be that fish, swimming upstream in a current that only gets stronger. There's no paradox here, no violation of causality. Information doesn't travel between us and galaxies beyond the Hubble sphere. We see their past light, emitted when they were closer, but we cannot send signals to them. We cannot reach them. They cannot reach us. The expansion has severed the connection, not by moving them away through space, but by expanding the space itself. Relativity is a local speed limit. Imagine a highway with a speed limit of 100 kilometers per hour. You can't drive faster than that. Your car is bound by the limit. But what if the highway itself is being stretched while you drive? The road lengthens between you and your destination. You're not speeding. You're following the limit. But the road construction happens faster than you can drive. The distance increases. You obey the speed limit, and you still never arrive. The limit applies to your motion through the road. It doesn't apply to the road itself being built. Space is the road. Galaxies are the cars. Relativity limits the cars. Expansion stretches the road. 2 points on opposite sides of a balloon. Draw them with a marker. Neither point moves across the surface of the balloon. They stay fixed in their locations. There's no speed involved, but inflate the balloon. The surface expands. The distance between the points increases. Inflate the balloon fast enough, and the distance can increase faster than light could travel across the surface. The points don't move. The surface does. No speed limit is broken because no motion through space occurred. That's the universe. We're points on the surface. The surface expands. The distances grow. And at large enough scales, they grow faster than light. Most of what you see in the night sky is already gone in this sense. Not destroyed, not collapsed, just beyond reach. The light arrived. The source is still out there, probably, but the connection is cut. The space between has grown too large. The expansion is too fast. You can see the galaxy, but you could never reach it, even in principle, even if you could travel at light speed, even if you had eternity to try. The universe isn't just expanding, it's severing itself, breaking into pieces that can no longer communicate. We live in one piece. We see the light from others, but the bridges are burning. And they're not burning because something moved. They're burning because space itself is becoming more space. Faster than light can cross it. The universe expanded, space stretched, and something remarkable happened because of it. Something we can still see today, if we know where to look. Actually, we don't even need to look. It's everywhere, all around you, right now. The oldest light in the universe, the most distant thing you could ever hope to see. 380,000 years after the Big Bang, the universe was still hot, unimaginably hot, about 3,000 degrees Kelvin. That's hot enough to melt tungsten, hot enough that the entire universe glowed like the filament of a light bulb. But it was cooling, expanding, and cooling. And at that specific moment, at that specific temperature, something changed. The universe became transparent. Before that moment, light couldn't travel. Not really. The universe was too hot, too dense. Every atom was torn apart into free electrons and bare nuclei. Photons would bounce off these free electrons constantly. A photon might travel the width of a room before scattering. Then it would bounce again and again. Light was trapped in an endless cosmic pinball machine. The universe was opaque, a fog so thick that no light could escape. Then the temperature dropped. Electrons slowed down. They started combining with atomic nuclei to form complete atoms. Hydrogen, helium, neutral atoms that don't scatter light the same way. The fog lifted, and for the first time, photons could travel freely. They were released. Prisoners set free after 380,000 years of captivity. Those photons have been traveling ever since. They're still traveling, right now, through your room, through your body, everywhere. That moment of release is called recombination, the time when electrons recombined with nuclei. Scientists also call it the surface of last scattering, the last moment when photons scattered off matter before flying free. And the light from that moment, that flash of transparency, is the cosmic microwave background, the CMB. It's the oldest light we can see, not just the oldest light we have seen, the oldest light we could ever see. Anything earlier than 380,000 years is locked away. The universe was opaque before that. There's no light from earlier times because light couldn't travel. You can't see through fog no matter how good your telescope. The CMB is the wall, the cosmic nursery wall. You're seeing the room you were born in, but before you could form memories. It's the earliest baby picture possible. When those photons were released, they were visible light, orange and red, like the glow of a fire. That's what 3,000-degree objects emit. But they've been traveling for over 13 billion years, and during that time, the universe expanded. Space stretched. The photons stretched with it. Their wavelengths grew longer, longer still, from visible light to infrared, from infrared to microwave radiation. The stretching factor is 1,100. The wavelengths are 1,100 times longer now than when they were emitted. That visible light is now microwave radiation, wavelengths of about 1 to 2 millimeters, and the temperature has dropped from 3,000 degrees Kelvin down to 2.725 degrees Kelvin, just barely above absolute zero. The universe has cooled. The expansion did that. The CMB is everywhere, perfectly uniform in every direction. Almost. It's uniform to 1 part in 100,000. That's almost smooth, almost featureless, but not quite. There are tiny variations, spots slightly warmer, spots slightly cooler, differences of a few millionths of a degree. Those tiny variations matter. They matter more than almost anything. Those little temperature differences were density variations, places where matter was slightly more concentrated, slightly denser, and those denser regions had slightly more gravity. They pulled in more matter, which increased their gravity, which pulled in even more matter. Over billions of years, those tiny seeds grew. They became stars, galaxies, clusters of galaxies, superclusters, everything, every structure in the universe, every galaxy you see, every star, every planet, all of it grew from those 1 part in 100,000 variations in the CMB. The map of the infant universe became the map of everything that exists today. The blueprint was written in light when the universe was 380,000 years old. We study this radiation carefully, very carefully. We've launched satellites dedicated entirely to measuring the CMB, precise instruments, sensitive detectors, billions of dollars spent, all to map microwaves from the beginning of time, which is important work, vital work. But here's the thing. Here's the part that gets me. This radiation is literally everywhere. You could detect it with sufficiently sensitive equipment in your kitchen. The echo of creation is in your living room right now. We send satellites into space to escape interference and get a clearer view, but the signal itself never left. It's been here the whole time, and you've seen it. You probably didn't know what you were seeing, but you've seen it. If you're old enough to remember analog television, you've seen the CMB. When a TV wasn't tuned to a channel, you'd see static, snow, white noise flickering across the screen, random patterns of black and white dots. About 1% of that static was the cosmic microwave background. Ancient photons from the infant universe were hitting your antenna, contributing to the noise. The cosmic origin of everything was hiding in the most mundane domestic technology. TV snow, that's where the Big Bang was. Right there on your screen. Those photons traveled for over 13 billion years. Through expanding space, through galaxy clusters, through the void, they passed civilizations that rose and fell, stars that were born and died, planets that formed and crumbled to dust, and they ended their journey as white noise on your television set. Think about that. The oldest thing you could possibly see, the most distant signal, the echo of creation itself, and it was part of the background hum of everyday life. You changed the channel to get rid of it. You adjusted the antenna to filter it out, but it was always there, a whisper from the beginning, telling us where we came from, showing us the universe as it was before stars existed, before galaxies formed, before anything we recognize came to be. That's what expansion gave us. Not just space between galaxies, not just redshift, but a window, a way to see back to the beginning. The CMB photons have been traveling so long, been stretched so much, that they carry information from a time we could never otherwise access. The expansion made them visible by changing their wavelength, and the expansion made them ancient by giving them time to reach us. The surface of last scattering is still out there. Actually, that's not quite right. The surface is a sphere around us. We're at the center. The CMB comes from every direction because the moment of transparency happened everywhere at once. We see a sphere because we're looking back in time. The farther we look, the earlier we see, and the CMB is as far back as we can look, 46 billion light years away now, because of expansion. But the light has been traveling for only 13.8 billion years. The space stretched while the light was in transit. We're surrounded by the echo, bathed in it. Every point in space sees the same thing, a faint glow from all directions, the after-image of the moment the universe opened its eyes. And every second, new CMB photons arrive, photons that took a slightly different path, that scattered from a slightly different location. The CMB isn't a static image, it's a continuous stream, a river of ancient light that never stops flowing. The universe became transparent once. It stayed transparent, and the light from that moment has been racing outward ever since. We catch some of it, study it, map it, learn from it, but most of it passes right through you, through the earth, through everything, heading out into the expanding cosmos, carrying the story of creation to places we'll never see, to futures we'll never know. That's the cosmic microwave background. Not just radiation, not just data, a messenger from the beginning, the earliest possible photograph of existence itself, still developing, still arriving, still teaching us what we are and where we came from. Right now, while you're listening to this, galaxies are disappearing from the universe, crossing an invisible line, an event horizon drawn not by gravity, but by expansion. Once they cross, their light will never reach us. No matter how long we wait, they're not being destroyed, they're just leaving, sailing past the point of no return while we watch. This is happening in real time, not in some distant future. Right now, the universe is already censoring itself, erasing its own history. Every second, more galaxies slip beyond the cosmic event horizon, the boundary where space expands faster than light can cross it. The information they carry, gone. The stars they contain, invisible forever. We can see them now, getting dimmer, redder, slower. Then they fade, then nothing. It's like watching books burn in a cosmic library before anyone gets to read them. Every galaxy that crosses that line takes its story with it, the elements it forged, the stars it birthed, the planets that might have formed. all of it becomes permanently unknowable. The universe is destroying information, and there's nothing we can do about it. Think about the local group, our gravitational neighborhood, the Milky Way, Andromeda, Triangulum, and a few dozen smaller galaxies, bound together by gravity. That bond is stronger than expansion. We'll stay together. Everything else is leaving. Picture lifeboats drifting on an ocean. You're in one. Your family, your supplies, everything you know. Other lifeboats float nearby. You can see them, wave to them, call out. They wave back. Then the current takes them. Slowly at first, then faster. You can still see them, but they're getting smaller. Their voices don't carry anymore. Soon they're dots on the horizon. Then they're gone. And eventually, you forget they were ever there. That's what's happening to the cosmos. Every galaxy outside the local group is another lifeboat drifting beyond rescue distance. We can still see thousands of them, millions, but one by one, they're crossing the horizon. In roughly 100 billion years, they'll all be gone from view. Every single one. The night sky will look different then. Empty, dark, just the merged remains of the Milky Way and Andromeda. One giant elliptical galaxy floating in blackness. No spiral arms in the distance. No galactic clusters. No cosmic web of structure stretching across space. Just us, alone, in an ocean of nothing. Any astronomers living then, roughly 150 billion years from now, would have no way to discover what we know. They'd look up and see one galaxy. Theirs. They'd see empty space in every direction. They'd measure the cosmic microwave background, but it would be so redshifted, so faint, they might not even detect it. And if they did, they couldn't interpret it correctly. Not without seeing other galaxies recede. Not without the evidence of expansion. They couldn't discover the Big Bang. The observation that led us to that conclusion, galaxies moving apart, would be impossible. All the galaxies would be gone. They couldn't measure the Hubble constant. They couldn't detect dark energy. They couldn't prove the universe had a beginning. Their observations would show a static cosmos, one island of stars surrounded by eternal void. And they'd be wrong, but they'd have no way to know it. The universe would be lying to them, not maliciously, just through the accident of timing. They'd build telescopes, run experiments, develop theories, all based on incomplete information, censored information, and their best models, built on their best observations, would point to a universe that never expanded, that always existed as it is, one galaxy, forever. We are cosmologically lucky. That's not an exaggeration. If humans had evolved 100 billion years from now, instead of 13.8 billion years after the Big Bang, we would know almost nothing. The evidence would be gone. Cosmology as a science wouldn't exist, because there'd be nothing to study, no distant galaxies to measure, no redshift to detect, no expansion to discover, just a lonely galaxy and a dark sky and a set of observations that told a completely false story. Our understanding of the cosmos depends entirely on when we showed up. We live in a brief window, a special epoch. The universe is transparent. We can see the cosmic microwave background, the afterglow of creation, and the universe is still populated with visible galaxies, thousands within reach of our telescopes, millions if we look deep enough. We can watch them move, measure their distances, map the structure of everything. This window won't last. It's already closing. The deep past was opaque. Before recombination, the universe was a fog of plasma. You couldn't see anything. No stars, no galaxies, no structure. Just light scattering endlessly through charged particles. Observers then, if any could have existed, would see nothing but glare. The deep future will be empty. After expansion carries everything away, observers will see nothing but darkness. Only now, in this thin slice of cosmic history, is the universe both transparent and full. We happen to arrive during the viewing hours, when the museum is open, when the lights are on. Future civilizations will arrive after closing time. They'll find locked doors and darkened halls. The exhibits will still exist, technically, out beyond the horizon, but unreachable, unseeable, as good as gone. That's what makes our existence so improbable. Not just that we're here, Not just that we're alive and aware and able to ask questions, but that we're here when the answers are still visible, when the universe still shows its history, when the evidence of the Big Bang, of expansion, of structure and evolution hasn't been erased yet. Every photograph we take of a distant galaxy is an act of preservation, capturing something that won't always be there. Every measurement of redshift, every mapping of cosmic structure, every detection of the microwave background. We're documenting a universe that's in the process of hiding itself, recording observations that future beings will never be able to make. They'll have to trust us. If any of our records survive, if any information makes it across that gulf of time, they'll read about galaxies and expansion and the Big Bang, and they'll have no way to confirm it, no way to check our work. They'll see one galaxy, their instruments will show empty space, and they'll have to decide whether to believe in a cosmos they can't observe or trust what their eyes tell them. That's solitary confinement on a cosmic scale. You're told a universe exists, told there were once billions of galaxies, trillions of stars, structure and light and motion, but when you look, you see an empty cell, 4 walls and nothing else. The universe exists, sure, out there, beyond the horizon, but you're locked in, and the door isn't just closed, it's moving away from you faster than you could ever chase it. We're on this side of the door, while it's still open, while we can still see out. That won't be true forever. The door is closing, slowly, but closing, and once it shuts, it never opens again. The previous section ended with a door closing, the universe pulling away from us, the view disappearing. But we haven't really asked the deeper question. Why is the door moving at all? Dark energy is just a name we gave to our ignorance, a placeholder. What's actually driving this? There are proposals, speculative, yes, but grounded in real physics, not science fiction. Ideas that take our current understanding and push it to places we can't yet observe. Some of these proposals suggest the expansion isn't happening because space contains something unusual. It's happening because space itself is something unusual. Start with this. Our universe might not be alone in its dimension. Some models propose our 3-dimensional space is embedded in a higher dimensional structure, a bulk, physicists call it. We can't see the extra dimensions. We're stuck in our 3-dimensional slice. But we might interact with the bulk, move through it, and that motion, that interaction, could appear to us as expansion. We're not expanding into anything we can see. We're sliding through something we can't. Picture a sheet of paper floating in a room. The sheet is 2-dimensional. Anything living on that sheet would only know length and width, not height. But if the sheet moves up or down through the room, beings on the sheet might detect effects, distortions, changes they can't quite explain. That's us, stuck on our sheet, feeling effects from dimensions we can't access. The math works. Extra dimensions show up in string theory, in attempts to unify quantum mechanics and gravity. They're not fringe ideas. They're consequences of trying to make the physics fit. Whether they're real is another question, but if they are, our expansion could be a side effect of existing in a space bigger than we can perceive. Here's another possibility. The baby universe hypothesis. This one sounds strange, but it comes from taking quantum mechanics seriously. Quantum fluctuations allow temporary violations of energy conservation. Tiny pockets of space can appear, exist for a fraction of a second, then disappear. That's established physics. The hypothesis extends this. What if some of those pockets don't disappear? What if they inflate briefly, forming microscopic universes, then merge back with our space? You wouldn't see them. They'd be smaller than atoms, smaller than anything we could ever detect. They'd form and merge instantly, but their cumulative effect could be measurable. Each tiny universe adds volume when it merges. Not much, but countless mergers, happening everywhere, all the time, could drive the expansion we observe. It's like rain falling on an ocean surface. The surface rises, but you can't see individual drops. You just see the overall increase in volume. The universe might be growing because it's absorbing its own quantum offspring, constantly, everywhere. Microscopic universes forming from nothing, living for an instant, then joining the parent cosmos. We'd never catch one in the act, but we'd see the result: space getting bigger. Not because something's pushing it, because it's eating its children. Think about that. The expansion might not need fuel. It might be self-sustaining, a consequence of quantum mechanics playing out at scales we can't observe. The math supports it. Whether nature actually does this, we don't know, but it's possible, and that's unsettling. The idea that entire universes could be forming and dying inside every cubic centimeter of space, and we'd never know. There's another scenario, the multiverse collision model. If eternal inflation is real, and that's a big if, then our universe is one bubble in a foam of bubble universes. Each bubble is a separate cosmos. Different laws, maybe, different constants. They're expanding into a larger inflating space. And sometimes, bubbles touch. Two soap bubbles touching don't merge. Not immediately. They push against each other. The boundary distorts. You can see the distortion pattern where they meet. Neither pops. They just reshape each other at the contact point. Multiverse collisions would work similarly. Two bubble universes interact. The collision wouldn't destroy either one, but it would leave a signature, a pattern in the cosmic microwave background, a cold spot, maybe, or a subtle alignment of temperature fluctuations. Some researchers claim they've seen these signatures. Others dispute the findings. The evidence is marginal at best, but the prediction is testable. That matters. This isn't pure speculation. It's speculation that makes predictions. If bubble universes collide with ours, we should see specific patterns in the sky. We've looked. The jury's still out. But the fact that we can look at all means this idea lives in the realm of science, not philosophy. The collision itself could drive expansion in our region, energy transfer at the boundary, momentum from the other universe affecting ours. It wouldn't be uniform. We'd see directional effects, a preferred direction in space where the collision happened. We do see some anomalies in the cosmic microwave background, a slight asymmetry, whether it's a collision scar or just noise in the data, nobody's certain. And then there's this. The quantum vacuum might not be stable. It has energy. We know that. Virtual particles pop in and out of existence. That's confirmed. But the vacuum might not be in its lowest energy state. It could be metastable, like water cooled below freezing but not yet frozen. It's ice waiting to happen. If the vacuum transitions to a lower energy state, everything changes. Not gradually, instantly. The transition would start somewhere. A bubble of true vacuum would form. Then it would expand at the speed of light. Inside the bubble, physics would be different. Particle masses would change. Forces would have different strengths. Everything that exists would be unmade and remade according to new rules. This isn't expansion, as we normally think of it. It's a phase transition, like ice melting. The melting changes the fundamental properties of water. It doesn't add something to water. It transforms what water is. A vacuum phase transition would transform what space is. The expansion we observe could be the early stages, a slow transition, or it could be stable now and transition later. We don't know. The math says both are possible. The comparison to ice melting only goes so far. When ice melts, you can still have ice in one place and water in another. A vacuum phase transition wouldn't work that way. The bubble boundary would move at light speed. You'd never see it coming. One moment, the universe as you know it. The next, gone, replaced by something else. And the expansion rate inside the new vacuum would likely be different. Maybe faster, maybe slower. Maybe the universe would collapse. This keeps physicists up at night. Not because it's likely, we have no evidence it's happening, but because it's possible. The universe might not be in its final form. It might be temporarily stable, and temporary could mean 1 trillion years or a microsecond. We can't tell from inside the system. These proposals sound different. They are different, but they share something. They all suggest expansion isn't about space moving into a void. It's about space responding to forces or structures we can't directly observe. Higher dimensions, quantum baby universes, bubble collisions, vacuum instability. The expansion is a symptom, not the disease. The real physics is happening at a level we can't access yet. The truth is, we're guessing. educated guessing, mathematically rigorous guessing, but guessing. Dark energy might be a cosmological constant, fine, but it might be something stranger, something that connects our universe to others, or to dimensions beyond our perception, or to the quantum foam underlying reality. We won't know until we gather more data, better measurements, new telescopes, different approaches. Maybe we'll find evidence for one of these ideas. Maybe they're all wrong. Maybe the answer is something nobody's thought of yet. For now, these possibilities sit on the edge of science. Testable in principle, untested in practice. They remind us how much we don't know, how many ways the universe could work that we haven't considered. The expansion is real. The observations are solid, but the why behind it remains open. And that opening is where physics lives. In the questions we can't yet answer, in the possibilities we can't yet rule out. The expansion tells us something profound about the nature of reality. When you run the math backward, when you reverse the stretching of space, everything converges, not to a point in space, to a point that was space. 13.8 billion years ago, the universe began, not as an explosion in an existing void, as the sudden emergence of space and time themselves from an unimaginably hot, dense state. That's what expansion implies. A beginning. The Big Bang wasn't a bomb going off in a pre-existing room. It was the creation of the room itself. Space, time, matter, energy, all of it, emerging together. Before that moment, there was no before, no place for anything to happen. The question, what came before the Big Bang, assumes time already existed. It didn't. We can't observe this beginning directly. We arrive at the scene 13.8 billion years late. The initial moments are gone. What we have instead is evidence. The cosmic microwave background, light from when the universe was 380,000 years old, the abundance of light elements like hydrogen and helium, forged in the first few minutes, the expansion itself still unfolding around us. From these clues, we reconstruct what happened. We're doing forensic science on a cosmic scale. The crime scene is billions of years cold. We piece together the story from what was left behind. Can we trust that reconstruction? That's a fair question. Every observation we make in cosmology is historical. Light takes time to travel. When you look at a distant galaxy, you're not seeing it as it is now. You're seeing it as it was when that light began its journey. The farther out we look, the farther back in time we see. Our entire picture of the universe is built from old light. We never see the present, only the past, layered at different depths depending on distance. This creates a strange situation. We're trying to understand the history and nature of the universe, but we're doing it with a sample size of one universe, observed from one location within it. We have no outside perspective, no external reference frame, no comparison case, no control group. You can't run the experiment again with different initial conditions. You can't observe the universe from outside to check your assumptions. If you could only observe one snowflake for 1 second of its life, could you figure out how snow forms, why it falls, and what winter is? That's what we're attempting with the universe. Think about the absurdity of it. All of cosmology, the entire Big Bang theory, our models of expansion and dark energy, the history of cosmic evolution, everything we think we know about the largest structures and longest timescales, it's all based on observations made from one rocky planet, orbiting one ordinary star, in one galaxy among hundreds of billions. We've been doing serious cosmology for less than a century. Humans have existed for a few 100,000 years. The universe has been around for 13.8 billion. We've observed it for a microscopic fraction of its lifespan, from a single vantage point, and we're claiming to understand its birth, its composition, and its fate. The hubris is staggering, and yet, the evidence keeps lining up. The cosmic microwave background matches theoretical predictions to extraordinary precision. The light element abundances fit models of Big Bang nucleosynthesis. The large-scale structure of the universe, the distribution of galaxies and voids, emerges naturally from small quantum fluctuations in the early universe, amplified by expansion. Independent lines of evidence converge on the same story. That convergence is why we trust the model, not because we can prove it absolutely. We can't, but because every new observation slots into place. This is how cosmology works. You can't do controlled experiments. You can't rerun cosmic history with different parameters. You observe what exists, build models that explain those observations, make predictions, then test them with new observations. When predictions fail, you revise the model. When they succeed, your confidence grows. It's science, but science under constraints that don't apply in a laboratory. You're dealing with a unique, unrepeatable event. The universe happened once. This is it. There's something both humbling and remarkable about that limitation. We have no right to understand the cosmos. We're pattern-seeking creatures on a small world, equipped with brains evolved to avoid predators and find food. Those brains weren't designed for cosmology. They were designed for survival on an African savanna. The fact that we can point telescopes at the sky, collect light from billions of years ago, and piece together a coherent history of everything, that's not inevitable. That's strange. The universe didn't have to be comprehensible. The laws of physics didn't have to be consistent across time and space. Mathematics didn't have to describe reality, but they do. And we can use that. The expansion itself is one of the clearest examples. Space stretches. We measure it. We quantify it. We trace it backward to a beginning and forward to possible futures. The observations are solid. The evidence is overwhelming. What expansion tells us is that space and time are not abstract containers for events. They're physical things. They can change. They can warp and stretch and curve. They had a beginning. They might have an end. That changes everything about how we think about reality. Space isn't just emptiness. Time isn't just a clock ticking in the background. They're part of the universe, not separate from it. They're woven into the fabric of existence, and that fabric can be pulled and twisted by matter and energy. The expansion proves it. You can watch space change in real time. We don't know what lies beyond the observable universe. We don't know if space is finite or infinite. We don't know what dark energy really is, or whether the expansion will continue forever. We don't know if there are other universes or higher dimensions or structures we can't even conceive of yet. Those are open questions. But we know the expansion is real. We know it started from a hot, dense state 13.8 billion years ago. We know the universe had a beginning. That knowledge, limited and incomplete as it is, represents one of the greatest intellectual achievements in human history. We looked up, measured carefully, thought deeply, and figured out where we came from. Not perfectly, not completely, but enough to know the story has a start. Enough to know we're part of something with a history, a trajectory, a fate, even if we're observing from the inside, even if we only have one universe to study, even if all our certainty is built on evidence filtered through billions of years of cosmic time. The expansion tells us reality itself is dynamic, not static, not eternal and unchanging, dynamic, growing, evolving. And that realization opens the door to everything else we've learned about the cosmos. The expansion continues. It accelerates. And if that continues, we know where this story ends. Heat, death. It's not a sudden event, not a catastrophe. It's a slow fade that takes timescales so vast they make the age of the universe look like a single breath. Star formation ceases in about 100 trillion years. 100 trillion. If you could live 1 million years, you'd need to do that 100 million times to reach the moment when the last stellar nursery goes dark. The universe will have aged 7,000 times longer than it's currently existed. And that's just when new stars stop forming. The stars that already exist keep burning for a while longer. The smallest red dwarfs sip their fuel so slowly they'll shine for another 20 trillion years after star formation ends. The last natural light in the universe won't go out until roughly 120 trillion years from now. Then darkness. Not the darkness of night, where you're just in a shadow. True darkness. Permanent darkness. No stars anywhere. The black holes remain. They'll be the last massive structures in existence. They sit in the void, pulling in the occasional stray particle, radiating nothing but the faintest whisper of Hawking radiation. The smallest black holes evaporate first. Solar mass black holes take 10 to the 64th years to disappear. The supermassive black holes at the centers of galaxies, the ones with billions of times the sun's mass, they last until 10 to the 100th years. That number is so large it has no human comparison. It's not like anything. It's just an incomprehensible duration followed by nothing. Even after the black holes evaporate, matter might not be stable. Protons might decay. We've never seen it happen, but some theories predict it occurs on timescales around 10 to the 34th years or longer. If protons decay, then atoms themselves fall apart. Every structure made of matter dissolves into lighter particles and radiation. The stars are gone. The black holes are gone. The atoms are gone. What remains? Photons, individual particles of light, stretched by expansion until their wavelengths span distances larger than galaxies. The temperature of space approaches absolute zero, not metaphorically, actually approaches it. The universe becomes colder than the hardest vacuum we can create in a laboratory. Emptier, too. Every structure that ever existed, every galaxy, every star, every planet, every atom, temporary. The natural state of the universe is this: eternal, frozen, expanding void. Everything interesting is an aberration. Think about that. Stars are aberrations. Galaxies are aberrations. Planets, life, consciousness, all of it. Temporary deviations from equilibrium. The universe's default state is maximum entropy. No energy gradients. No fuel for any process. No way for anything to happen. It's like a party where everyone slowly walks to opposite corners of the room and stops talking. The people are still there. The energy still exists. But no interactions are possible. No one can reach anyone else. Silence. The final photon travels through space that's expanding faster than it can ever cross. Its wavelength stretches until it becomes indistinguishable from the vacuum itself. It's the last letter ever written, traveling forever with no one to read it. Information eternally preserved, but Yongyuan-ni meaningless. There are no observers left to witness this final state. No consciousness anywhere to know the universe still exists. We asked, at the beginning, what the universe expands into. We called it a broken question, one that assumes something outside when there is no outside. The question doesn't work because it relies on intuitions that don't apply. The expansion itself will break everything else. It will break apart the galaxy clusters, already happening. It will break apart the galaxies themselves, scattering stars into the void. It will outlast those stars. It will outlast the black holes. It will stretch space until even the concept of meaning becomes too diluted to hold together. The ultimate consequence of expansion, if it continues, is the end of structure itself, the end of change, the end of time having any significance. We live in the aberration. We exist during the brief cosmic moment when stars shine, when galaxies cluster, when complexity is possible. Before us, the universe was too hot, too dense, too uniform. After us, it will be too cold, too empty, too stretched. We're here in the narrow window when interesting things can happen. That's not depressing. That's not nihilistic. That's context. Knowing the universe has this fate doesn't diminish the present. It clarifies it. We're part of something temporary and precious, not despite its impermanence, but because of it. The expansion that will eventually erase everything is the same expansion that made everything possible in the first place. The cooling, the structure formation, the stars, us. The universe is expanding into nothing because there is no into. It's just expanding, creating more space, more distance, more isolation, and eventually more silence than anything has ever been silent before. But not yet, not for a very long time. Right now, we're still here, still looking up, still trying to understand what it means that reality itself is dynamic, growing, unreachable at its edges, and Yongyuan-ni beyond complete knowing. We figured out the expansion from the inside, with limited tools, with one universe to study. And that might be the most remarkable thing of all. Not that the universe is expanding, but that we noticed.